Hey there everyone, this is Hanson here. Today we begin a next chapter called Carboxylic Acids, Esters, and Amides. Just thinking about how that continues from our previous chapter where we studied ketones and aldehydes. We know that the ketone, of course, had the ROR function there with the carbonyl carbon. And if it was at the end of your terminal chain, we called that an aldehyde. But the functional group of the carbonyl carbon here, C double bond O, that functional group carries forward with us, looking at other ways we can find a carbonyl carbon, carboxylic acids, esters, and amides. So the work continues with that C double bond O. As we take a peek at the topics ahead of us, we begin with looking at the structure and bonding of these acids, esters, and amides. We practice nomenclature and physical properties. We have highlighted in red some assigned reading sections from your note pack. Interesting carboxylic acids in the consumer products and medicines, interesting esters and amides, assigned reading, the focus in health in chapter 7 or section 7, and again down here specifically about penicillin in terms of applications of carboxylic acids, esters, and amides. We'll look at some pH chemistry with the acidity of carboxylic acids. Thinking about the acidity, the ionizing proton is this guy right here, the COOH. This is your proton that we'll investigate in acid-base chemistry. And further reactions that we'll look at are on hydrolysis of esters and amides, adding water across that bond and looking what happens when we add alcohols across there as well. And then really just applications as well in terms of polymer science, polyamides, and polyesters will all be discussed. So just mentioning what's in red is the assigned reading. What we'll study on is in the green. And again, the chemistry part, the acidity and hydrolysis reactions. These are our learning goals for our chapter. I want you to be able to identify the characteristics of carboxylic acids, the esters, and amides. We'll have to practice nomenclature. We'll give useful examples of all three functional groups. We'll draw acid-base reactions for those carboxy acids. Saponification. This is actually part of a lab goal as well in 1540. Saponification, how to soak clean dirt away. Acid-base chemistry of aspirin, converting carboxylic acids into esters and amides. What does it look like to hydrolysize esters and amides, and draw the structures of polyesters, polyamides, and explain how penicillin works? So let's get started, shall we? The first we'll do is just draw a general structure for these compounds. And the first general structure we'll look at is the carboxylic acid, the COOH. And you hear me say COOH to represent that, a carboxylic acid. Notice that these are always at the terminal end of a carbon chain. The terminal end is this carbon right here from a longer carbon chain. The carboxyl group is the COOH, and as an example of a carboxylic acid, we could look at a 2-carbon chain and call this acetic acid. Looking at the acetate polyatomic ion, CH3COOH, acetic acid. The carboxylic acids sometimes are abbreviated as RCOOH or RCO2H, and that's a bullet point under the drawing that you just met. So carboxys, COOH, COOH, or you might see those oxygens with a subscript of 2. A second functional group we'll be studying this chapter is the esters. The esters are carbonyl compounds that contain an OR, which is known as an alkoxy group, bonded to the carbonyl carbon. So this is the difference right here. Carboxylic acid had a hydrogen there. The ester has another carbon chain, meaning that these are always interior, where the carboxylic acids were always at the end of the chain. Here is an example. You would simply name this methyl. Here is the methyl part of the name. And then here's the 2-carbon parent name from the carboxylic acid was, remember from the previous slide, the parent name acetic acid. So now we have acetate. We'll learn The ick will turn to ate. We'll learn that in our very next practice. The esters are abbreviated RCOOH. It's that alkoxide group bonded to another carbonyl atom, and they have an abbreviation as COR, C-O-O-R, and that's another bullet point down there. And our third and final functional group for this chapter are the amides. These are carbonyl compounds that contain a nitrogen atom bonded to the carbonyl carbon. So right next door, we have a nitrogen. And we will learn that carbonyl carbons bonded to a nitrogen with one hydrogen in each direction. Notice there'll be a lone pair. These will be called primary amines. And we will learn that if the nitrogen bonded to the carbonyl is bonded to another carbon as well, these will be called secondary amines. And just as you suppose, we could have the nitrogen bonded in all directions to carbon atoms, and you would have then a tertiary amine. That's a lone set of dots. So we'll write those into our notes as well. And you can see here the primary amide. The amide itself is when it's next to a carbonyl carbon. Now, an amine does not have an oxygen nearby. An amide has a carbon directly next to it. So I wanted to clarify amine from amide. Just as we had primary, secondary, and tertiary amines from a previous chapter, we will also have primary, secondary, and tertiary amides in this chapter. But the location that makes this difference is that this ammonia group, this N group, is directly next to a carbonyl carbon. Amides are classified based on the number of carbon that they are bonded to. So find your nitrogens and count how many bonds lead to carbons. Now remember, nitrogen itself is in group 5A, so we'll have 3 bonds and a lone set of electrons. That's what nitrogen needs to have a complete octet. So the set of nitrogen electron pair plus the 3 bonds completes its octet. When you find your nitrogen, and I'll highlight the nitrogen here in, let's say, a nice yellow color, how many of its 3 bonds lead to carbon? And in this example, there's just 1. So we labeled that as a primary amide, contains just 1 CN bond. And notice how we abbreviated it here, RCONH2. That's its abbreviation, RCONH2. In a secondary amide, find your nitrogen and count how many carbons it's attached to. It will always be attached to at least 1. If 2 of the 3 nitrogen bonds leads to other carbons, we call it a secondary amide. And that gets abbreviated RCONHR prime, where R prime is the carbon chain that's coming off of the nitrogen. And then here again is our tertiary amine. Here's the nitrogen. How many hydrogens does it lead out to? How many carbons? 1, 2, 3 different carbons. And therefore we can see that this would be a tertiary amine. All 3 bonds of the nitrogen lead out to other carbons. So in our notes we wrote down primary, secondary, and tertiary amide and found their formulas, their general formulas, by the number of carbons that the nitrogen attaches to. Cyclic structures. Cyclic structures occur as well. Let's take a peek at a cyclic ester, which would be called a lactone, and a cyclic amide, which would be called a lactam. When we draw, notice here we would have a 5-membered ring, And in that 5 member, here is your carbonyl carbon. That's your carbon attached to a double bond to oxygen, which also leads out to an oxygen from the other direction. So this carbon is attached double bond this way and a single bond this way. That is a cyclic ester, a 5-membered ring where we still have C double bond O, R on either side. It's just that these R's are attached to each other in a cyclic ring. And a lactam is the name given to a cyclic amide. Remember what an amide is: a carbonyl carbon attached to a nitrogen. It's just that now these 2 carbons end up to be in a cyclic structure. That cyclic amide is called a lactam. The carbonyl carbon is bonded to a nitrogen that's part of the ring. The ring includes the nitrogen. The ring above included the oxygen. Carboxylic acids, esters, and amides all contain the acyl group, ACYL, the acyl group. And you hear that called RCO. Now to just picture that, R connected to the oxygen, connected to something else. And this right here determines what functional group you're looking at. If this is an OH, we know to call it a carboxylic acid. If that is an OR, and I'll put a prime there so you know it's different than the other carbon here, you know to call it an ester. And if it's an NH2 or some derivative there, you know to call it an amide. So looking at the next door also lets you figure out what functional group you have. But if you'll allow me, I'd like to bring in last chapter as well. Remember this also, this very position determined 2 other functional groups. If it was an H, we called it an aldehyde. I don't want you to forget those. And if it was another R, we called it a ketone. Just to remember those 2 functional groups as well. All goes by the position directly to the right of the carbonyl carbon, the acyl group, RCO. The carbonyl carbon is trigonal planar, so all bond angles are exactly 120 degrees. Trigonal planar means it lies flat on the table, and this is an equilateral triangle between all 3 of those bonds. We will also see the oxygen being much more electronegative than the carbon, so we can see that this bond is very polar as well. The carbonyl group is polar. That tells us the oxygen is very electron rich. Remember, these are electrons up here, so we have a very rich electron cloud. And that the carbonyl oxygen, carbon itself, would be electron deficient. This will play a role in a later lesson when we talk about physical properties. Seeing that it is polar, we know that it would exhibit dipole-dipole interactions. And we'll talk about, depending upon what this guy is right here, maybe we could even have some hydrogen bonding interactions. So we'll look at physical properties, not only of the carbonyl carbon, the C double bond O, but as well as the neighbor functional group to determine how sticky, how attractive are those molecules to one another. For now, let's keep practicing recognizing the functional groups. Let's try to draw out each compound from their condensed formulas and then label those as a carboxylic acid, ester, or amide. Well, my eyes go right here to this particular section first, and what I'm going to say is that's the part that gives me this linkage. And then I want to decide what's on this side, and then I have to decide what's on this side. So that is the kind of the game here, is deciding what we see on each side of the carbon double bond oxygen. To the right, I can see a 2-carbon chain, so I'll have CH2, CH3. And to the left, I have the same idea. I have a CH3, CH2, and those are the linkages across to the carbon. Notice that this would be an R, And then over here is another R. And so if you think about the general formula, you'd have RCOOR prime. And of course, that is what we refer to as an ester. Letter A is an ester. Here's what interests me in letter B. I have the C double bond O, but it's next door to a nitrogen. See this? That's the interesting part. Next door, I can see a methyl group to the left. That's this part. And then on the nitrogen, remember nitrogen has 3 bonds. One of them leads directly back to the carbonyl, C double bond O, but it has 2 other extensions. One of them leads to a hydrogen, the other leads to a methyl group. This is what we would call a secondary amide. The nitrogen is attached to 2 other carbons. How about letter C? Well, I'm looking at this end, COOH, so I can automatically recognize I'm going to have a carboxylic acid functional group. The carbon that's attached to the COO is attached to 3 other carbons. So there's my structural formula. And just thinking about electron sets, this of course would be a carboxylic acid. And there's a letter D as well. In letter D, what do we notice interesting? Oh, here I find a nitrogen. So this is telling me for letter D, I have a carbonyl carbon, and next door is to a nitrogen. Remember, nitrogen needs 3 bonds, and it looks like 2 of those are methyl groups. And how about left side of the carbonyl? Well, I can see it has a carbon, and then attached to that is 2 more carbons. So there's our structural formula here. Of course, this would be called an amide. And I can actually count 1, 2, 3 carbons. We could recognize that as a tertiary amide. How'd you do? Should we try another? Why don't you pause and give yourself think time? Classify the 4 amides as primary, secondary, or tertiary in this particular hormone. Are you ready to check? Well, let's do it. Here's a nitrogen. I'll just find the nitrogens first. I can just highlight all the nitrogens. Now remember, to be an amide, we need this functional group. We need it to be right next door to the carbonyl oxygen there, C double bond O. And so out of these, let's eliminate what's not next door to a C double bond O, and that's this guy, and that's this guy. So that when I'm really focusing in on making sure I have, I don't know why I changed marker color. When I want to make sure it's next to a C double bond O to meet the qualifications of being an amide. So I can count 1, 2, 3, 4 different amide groups. Now let's classify how many, are primary, secondary, or tertiary. So just remember, it's kind of an easy way to do it is to count hydrogens. A primary amide has 2 hydrogens. Here's one with 2 hydrogens. That's a primary amide. It's the only one I see with 2 hydrogens. A secondary amide, remember, nitrogen needs 3 bonds. So if one of those is attached to a carbon, only one is left for a hydrogen. So here I can recognize 2 H's. Here I recognize just 1 hydrogen. That didn't come out right. 1 hydrogen. Do we see any like that? Here's one. That would be a secondary amide. Here's one. That would be a secondary amide because it's attached to 1 hydrogen. And in the last example, just to emphasize, when you see RC double bond O, and if all hydrogens are removed, then this would be called a tertiary amide, which is no hydrogens left at all. And that one I can see right here. That's a nitrogen attached to 3 carbons. Secondaries, nitrogen attached to 2 carbons. And primaries are attached to just 1 carbon, and that's always the carbonyl carbon in your compound. Let's label each functional group in lisinopril, a drug that's used to treat high blood pressure. How many trigonal planar carbons does lisinopril contain? Give yourself think time. I'm encouraging you to pause the video, think this through, and then come back to me. Okay, well, let's take a peek at what we find. Anything interesting? Well, let's find all the functional groups, and I'll just kind of go from left to right. One of the first functional groups I notice is this guy. This is an aromatic ring. That's commonly called benzene. It's an aromatic part of the compound. What else do I see? How about COOH right up here? See that C double bond O to OH, just so you can see how that really is written out. In yellow, that's a carboxylic acid. What else? Well, here I notice that I have a nitrogen. That looks pretty interesting. I'll highlight that one in pink. That nitrogen is not next door to a carbonyl carbon. So right here, this is called an amine, not an amide, but an amine. As a matter of fact, it would be called a secondary amine simply because it's attached to 2 other carbons. Now I can find, if I really start putting colors here, how about blue? Here's an interesting spot. A nitrogen directly next door to a carbonyl carbon. This is an amide functional group. The nitrogen is attached to 3 other carbons, so this is actually a tertiary amide. Do you see other things? How about right here? If I were to highlight that color, I was trying to highlight this guy right here. That's an interesting part of the molecule. I would say, well, I have that as an NH2. It's not next door to a carbonyl, so this is an amine, and it's actually a primary amine. Anything else? Oh, I do see one more. How about, let's try to find an imaginative color right here, this guy. This would be classified as a carboxylic acid. See that COOH? So that's your carboxy acid. Did you find them all? Did I miss any? I think all the others look kind of like boring hydrocarbon chains. All right, good work. Let's go to work with our nomenclature skills, taking each one of the functional groups and practice naming it. Let's start with the first of the 3, carboxylic acids. It says, to name a carboxylic acid using the IUPAC system, we have to find the longest carbon chain that contains the COOH. And this right here will always be carbon number 1 because it's at the terminal end. Remember that COOH is at the end of the chain, and therefore it will determine carbon 1. From the parent chain, we change the E from the parent to an oic acid. And I don't have to tell you it's number 1 because carbon COOH is always carbon number 1 in the chain. And then we just apply all other nomenclature rules. Shall we try one? Let's look at this guy. Oh, I wanted to do some vocabulary. Thank you. I just noticed that. The vocabulary check. The carbonyl carbon is our focused functional group here. And that really is called the acyl group, right? Carbonyl carbon is this guy here. The carbon that is directly next to the carbonyl carbon is called an alpha carbon. And second position over would be called a beta carbon. So if I think about that, I would have, let's say, I'll just make one up like this. How about if we just did this? Notice that we would highlight the carbonyl carbon first, and that simply becomes where the point of reference is. Directly next to the carbonyl carbon is the alpha carbon. So that right there would be labeled alpha. And any carbon directly next to the alpha carbon would be labeled beta carbon. And so this would have 2 beta positions. If I actually had another carbon up here, because there could be a 4th bond, that would be an equivalent beta carbon. So I just wanted to emphasize that vocabulary. Alpha and beta represent the positions that are next door to the carbonyl carbon. Now let's practice a carboxylic acid name. First of all, our functional group right here gets priority. There's your COOH, carboxylic acid. So that means this guy is carbon number 1. Let's make that a color so we can see. Carbon number 1, then carbon number 2, here's 3, here's 4, here's 5, here's 6. So the longest parent chain, 1, 2, 3, 4, 5, 6. That means our parent word is going to be hexane, the parent, except then it says take the E off and I want you to turn it to hexane-oic. That the E converts to oic, hexane-oic acid. Anything else interesting about that? Oh, I see some substituent branches. At 4, 5, we have a methyl group. We have 2 methyl groups, so I'll put 4,5-dimethyl hexanoic acid, and that should be all one word. So how does that feel? Hexane simply becomes hexanoic acid, and just simply number the branches from there. I'd also like you to know some simple carboxylic acids by their common names. For instance, formic acid has just 1 carbon. Do you remember formaldehyde was the simplest aldehyde? We call that formaldehyde. And there is no 1 carbon ketone. That's by law, there's no definition of a 1 carbon ketone. So we had a couple of examples with form representing 1 carbon. Then in this example, we have a 2 carbon acetic acid. Acetic acid. Now if we had a common name, acetic acid, it would also have an IUPAC name of ethanoic acid. This would have a IUPAC name of methanoic acid. 1 carbon. But it has a common name as well. And then here, the benzoic acid is the IUPAC name for the benzene ring with the COOH attached to it. There's your benzoic acid. You need to draw those and really commit those to memory because they will become parent names when we're using carboxylic acid nomenclature. Should we practice? I'd like you to think through. Try these on your own, practicing, give yourself think time, and when ready, turn on the video and see how well you did. There's a whole series of them, so let's take these and I'll just start working them. Letter A, I find a 6 carbon chain, so I know that the root word will be hexane-oic acid. I see methyl groups at carbon 3, so I would have 3,3-dimethyl hexanoic acid, all one word, hexanoic acid. Carbon number 1, 2, 3, 4, 5. Carbon 1 is always the carboxylic acid, so my parent name is pentanoic acid. What else do we see? Oh, I see a substituent branch. I would see at carbon 4, we have chloro. 4-chloropentanoic acid. Doing well? Let's keep going. 1, 2, 3, 4, and then we have a branch, 5, 6, and it's like this guy coming up again. You see how that worked? We had 1, 2, 3, 4, 5, 6 carbons in the longest chain. There's your COOH at carbon 1. At carbon 2, there's an ethyl group. At carbon 4, 1, 2, 3, 4, carbon 4 was attached to 2 ethyl groups. It's kind of looking like in terms of the branching. We have a parent name of hexanoic acid. At carbon 2 and 4, there's diethyl. So 2,4-diethyl hexanoic acid. That's our name. How fun is that to say? Keep trying. I put on a bunch because practice makes permanent. Let's try figuring this guy out. Here's 1, 2, 3, 4, and then this is taken twice. So this carbon number 4 it has a carbon coming off in either direction. So do you see that? Here's carbon 1, 2, 3, 4, and then carbon 4 had 2 methyl groups off of it. So that's what I'm looking at. At carbon 4, there's 2 methyls. So 1, 2, 3, 4, 5 carbons in the longest chain, and at carbon number 4, there's a methyl group. How about letter B? 1, 2, 3, 4, 5, 6, 7, 8. Longest carbon chain that contains the COOH is an octanoic acid. Well, carbon 4 and carbon 5 both have ethyl groups. How about 4,5-diethyl octanoic acid? Sweet. Now we have to start carbon 1, 2, 3, 4, 5, 6, 7. At carbon number 2, I see a 2-carbon branch, so there's your ethyl, and a 7-carbon parent chain, heptanoic acid. Beautiful. I bet you're doing great. There's more. This is our next set. 1, 2, 3, 4, 5, 6, 7, 8. This branches up. So that would be 7-methyl octanoic acid. 1, 2, 3, 4, 5, 6. We have 3, 4, 5 trimethyl, and then hexanoic acid. Oh, how you doing? Are you in a home stretch? 1, 2, 3, 4, 5, 6, 7. 2-methyl heptanoic acid. Give yourself a big old smiley face. It just feels good. The last part, we had to go from the words to the structure. So that's not too tough. You want to find the root word. Here's butanoic acid. So that tells me I have a 4-carbon chain. And at carbon number 1 is always the carboxylic acid functional group. And at carbon number 2, I would have a bromine. 2-bromobutanoic acid. Perfect. How about B? Here we have a pentanoic acid. So let me just draw 5 carbons. Of course, carbon 1 is the carboxylic acid, COOH. And then at carbon 2 is a methyl group. And at carbon 3 is a methyl group. 2,3-dimethyl pentanoic acid. How about letter C? We have an octanoic acid. 1, 2, 3, 4, 5, 6, 7, 8. Carbon number 1 always is the COOH, COOH. Carbon 1. Carbon 2 has an ethyl group. Carbon 5 has 2 methyl groups. And I think we got it. 2-ethyl, check. 5,5-dimethyl, check. Octanoic acid, we did it. And how about a letter D? Here we have decanoic acid. That's 10 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Long carbon chain. Carbon 1, of course, is the COOH. So there's carbon 1 at the back of the position here. Let's count to carbon 3, 4, 5, 6. Those things have tetraethyl. Tetraethyl. So there's a 2-carbon chain at carbon off carbon 2. No, not carbon 2, Linda. Silly me. There's a tetraethyl starting at carbon 3. There's an ethyl group. At carbon 4, there's an ethyl group. At carbon 5, there's an ethyl group. And at carbon 6, there's an ethyl group. And I just made mine go up, down, so it wasn't so crowded. So just kind of consider as you're attaching those, make sure the bonds are actually there. And we have our 3, 4, 5, 6 tetraethyl decanoic acid. Sweet. Let's turn our attention to a second functional group, practice naming esters, the RCOOH. Now the esters are derived from the names of the parent carboxylic acids. Remember formic acid? We should draw that again because repetition helps remember. Draw in formic acid. That's a 1-carbon carboxylic acid. Second one we should just remember is acetic acid. And the third is benzoic acid. These names are given as IUPAC names, but are rarely used. So let's use the common names for those particular structures. Alrighty, so that was just a review from a previous page. Here's how to name an ester. You want to locate the alkyl chain connected to the oxygen atom and name this with an YL ending. Let's just suppose I make one up here and I go 1, 2, 3, just to kind of remember. That would be an example of an ester. So what I'm saying is part number 1, for step 1, we want to locate the R group, the alkyl chain that's connected to the oxygen atom directly there. So not the carbonyl carbon, but on the opposite side of the oxygen. And this would just be called methyl. If you had a 2-carbon chain at that location, it would be ethyl, propyl, butyl, and so forth. So we'll name the alkyl chain connected to the oxygen just by ending a YL. And then you locate the alkyl chain connected to the RCO group. And so thinking about what that just said, in terms of highlighting, the other part of the functional group would be this part. That's going to be derived from the parent carboxylic acid group. So let me just clarify that. A moment ago, we named a 3-carbon chain with an OH as propanoic acid. What we're now being told to do is still use that root word from the carboxylic acid parent, but instead of using OIC, you take off IC and you put 8. IC turns to 8. So this would now be called propane O8. Here it's a double vowel. Propane O8. Propane O8. And of course the acid gets dropped as well. And then you just simply put the names together. The alkyl group comes first, methyl. Then the parent propane O8. The name of that ester, methyl propane O8. Let's practice. That sounds like a mouthful, doesn't it? Let's practice. Let's name this compound CH3, CO2, CH2, CH3. Okay, let's figure out the structure first. Right here is kind of the basis of the structure where I have an C double bond O and next to it is another oxygen. This is the ester linkage, if you will. On this side, I see a 2-carbon chain, and on this side, I see 1 carbon to the left there of the carbonyl carbon. So this is my structure, CH3, CO2, CH2, CH3, just to kind of see how that's put together. The first thing I want to do is to locate the alkyl group. And the alkyl group is always directly next to the oxygen in that carbon chain. So this will be called ethyl. Then locate the original carboxylic acid. This would have been called a 2-carbon chain. Do you remember just from a moment ago what 2 carbons was called? It was called acetic. Let me go back and just show you where you wrote that. Acetic acid. Now remember how to change the rules here. The ic turns to 8. Ic turns to 8. And this becomes ethyl acetate. Now, I have a very important fix in your notepad, and I just did it automatically here. I'm going to highlight this very carefully. Right here, I made a mistake in typing your notes because we do not change the oic, we just change the ic. Can you please, the bottom of page 6 in your notepad, I need you to repair something with me. Oops, you want to come up? Come on. Oops, I just had to pick up my dog. He's in my lap now. I want you to cross this off. That's a mistake. And now what that means is that's not oxygen. It's just cross off the O. The rule should say turn ic to 8. Not oic, but just ic to 8. So with that repaired, we named ethyl acetate. And that's the name of that structure. So locating the alkyl chain and changing it to YL, locate the carbonyl carbon and name from the carboxylic acid parent, changing ic to 8. Make sure you repair that in your notepad. Thank you. So let's practice. Let's name some esters. So I like to just kind of figure out what it looks like. My eyes go right here, first of all, and I get that set up. I have C double bond O leading to an oxygen. On this side then, there's 1 carbon group. And on this side, there's 4 plus 1 more is a total of 5. 1, 2, 3, 4, 5. 5 carbons there on that side. So the first thing we want to do, let's locate the alkyl group. And that alkyl group is attached to just the oxygen side, and this would be called methyl. On this side, we want to locate what we would call the carboxylic acid parent. So this would have 1, 2, 3, 4, 5, 6 carbons in that carboxylic acid parent. It would have been named hexaneoic acid, but I'm trying to make sure you see we just take the ic off and turn to 8. We don't take oic. We leave the O there. Ic turns to 8. Put it together. The alkyl group comes first. This is methyl. And then you write hexaneO8. Methyl hexaneO8, the name of that ester. All right, let's try letter B. Here's our structure for B. We have the aromatic compound, and then it has an oxygen leading out to 2 more carbons. And so when I look at this, the alkyl group is an ethyl group. The parent carboxylic acid is called benzoic acid. Put this together and we have the ethyl first, and then benzoate, ethyl benzoate. Ic turns to 8. And letter C is drawn so nicely for us already. Here is a 1, 2, 3 carbon chain, so that would be propyl. And here is a 1, 2, 3, 4, 5, so propanoic acid. Or I'm sorry, that was 3. Pentanoic acid. Now remember, the original carboxylic acid would be pentanoic. The alkyl group is a 3 carbon chain, so it's propyl. Let's put it together and we would hear it called propyl, and then pentanoate. That's your ester's name, propyl pentanoate. So letter A, methyl hexanoate. Letter B, ethyl benzanoate. And letter C, propyl pentanoate. Leave the O, just turn the ic to 8. Let's try some amides. Now, amides, they get a little tricky just in the sense that we have to figure out how many groups are attached to the nitrogens. So all primary amides are named by replacing the oic acid with amide. Now, let's emphasize the O is included in this particular conversion. Include the oxygen. And I keep saying the oxygen. Include the O in the word, oic. And just change it to amide. So a moment ago, this would have been, as the parent carboxylic acid, we would have called this acetic acid. So this becomes acetamide. This had no O in it, right? This is no O, so there's no O to convert. Now notice here, a moment ago, we would have called this, with the aromatic ring, COOH, right here, this would have been benzoic acid. But now we're taking the oic off and we get benzamide. So we're replacing the oic from the parent carboxylic acid and just putting the term amide there to let you know there's a nitrogen linkage. Now primary amides are quite nice because they're attached to just hydrogen, so I don't have to worry about any other alkyl group. However, when we have a nitrogen that's either secondary or even tertiary, we have to include the alkyl groups that are attached to the nitrogen. So remember, a nitrogen needs 3 bonds. One of them will always be to the carbonyl carbon. That's what's making it the amide. If these are both hydrogens, there's no need to tell you what the alkyl group is. A primary amide, I just take the word from the parent acid and put the amide on it. But now all of a sudden, if I have a secondary amide, which would look like the nitrogen attached to just one hydrogen and now some kind of R group, I have to tell you what that R group is in the name. And if I have a tertiary amide, I'd have to tell you what both of these alkyl groups are in the name. So naming primary amides, very simple, very straightforward. Naming the secondary and tertiary amides are a little more challenging. So let's focus here on what we said is the primary amide. You naming those 2 structures, you called it acetamide. Hear that name, acetamide. And this is benzamide. And in the next structures, we're looking at systematic names for naming these groups that have N's on them, right? The secondary and tertiary amines that have to be given names. So give a systematic name for each amide. And as I look at the example, here's our step-by-step process. In the first example, I want you to notice right here is the original carboxylic acid would have had one carbon. A one carbon carboxylic acid was called formic acid. So we take the ic acid and put amide, but I still have to tell you about this alkyl group. The prefix N is now going to be used to tell you the name of the alkyl group attached to that hydrogen or to the nitrogen there. This is called an ethyl group because it's 2 carbons long. N-ethyl form amide. That's the answer to letter A. Notice in letter B, we said the parent name was benzamide. But now, of course, there's 2 attachments to the nitrogen, so N, N, dimethyl benzamide. We have to let you know what the alkyl groups are on the nitrogen, and you do so by just using a letter N to designate the attachments. So let's try some of these. Name the alkyl group bonded to the nitrogen atom using the prefix N to precede the name, and then name the acyl group with the suffix amide. Give an acceptable name for each. So this is looking back in the notepad page, and we're trying to just practice some amides. Well, first of all, I recognize this as a primary amide, so I don't need any N's for prefixes. I have 1, 2, 3, 4, 5. The original name would have been pentaneoic acid for the carboxylic acid functional group. But instead of having the oic acid, I'm letting you know that it's attached to nitrogens, and I just say that as saying pentane amide. And there's no N's to attach, no prefixes, because all of these, they have no alkyl groups. They're all hydrogens. Now here, the parent name of this carboxylic acid was benzoic acid. So I can see the parent name becomes benzamide. However, now I see that there's one alkyl group to name that's attached to the nitrogen. And so to do that, you'll do N to let you know it's the attachment on the nitrogen, and it becomes methyl benzamide. Now here, this was a secondary. Here is a tertiary amide. Here's the parent carboxylic acid. This would have been named formic acid, one carbon in that group, formic acid. A tertiary amide that has 1, 2, 3 carbons, so that's propyl, and they're both identical. So that nitrogen with 3 bonds, one of them is leading out to a propyl, the other is leading out to a propyl, and the other is leading back to the original carbonyl carbon. So I have to let you know that both of these groups are propyl that are on the nitrogen. And so I'll do that by saying N, N dash dipropyl form amide. Should we try another? Let's draw the structure of each amide. Well, here I can see propane amide. So propane, that's a 3-carbon parent, and I don't see any attachments to that a nitrogen. I don't have any N's in front of it to tell me alkyl groups. So I simply have a 3-carbon chain. That was the original carboxylic acid ending with NH2, propane amide. Letter B, here I see hexane amide with an N-ethyl. Well, the parent here is a 6-carbon chain. At carbon number 1, of course, is the carbonyl, and then it leads out to a nitrogen. Nitrogen has 3 bonds and a set of dots. We know that. One of them will be an ethyl group, and the other will just be a hydrogen. So there's our structural formula for N-ethyl hexane amide. And then that's the ethyl part. So here's your ethyl, and that's your hexane amide on the other side. How about C? Dimethyl acetamide. Okay, well, acetamide we know to be a 2-carbon parent, and right next door to that would be the nitrogen. Nitrogen has 3 bonds. One of them is going to a methyl, and the other is going to a methyl. So that's N-dimethyl acetamide. And there's one more, letter D, N-butyl and methyl butane amide. All right, well, the parent is butane, and there's the nitrogen linkage, and then nitrogen has 3 bonds. Each of those is attached to a 4-carbon unit. So there's our not each of them, that's a repair, sorry. One of them is a butyl, the other one is a methyl. One, two, three, 4. There is N-butyl, N-methyl, butane amide. I got it. 4 carbons in the parent chain, butane amide, and then there's the methyl, and there's the butyl. Got it. We did it. Say, I wanted to be sure to back up. I think I missed a slide right here, and perhaps you filled it in, but I want to be sure that I don't leave any gaps in your instructions. So I'm going to draw these for you corresponding to the name. So just to kind of figure out, these were esters, and I might have missed that particular section. So give yourself some feedback and check those. Propane-08, so I can see that I have a 3-carbon original carboxylic acid, 3-carbon, and then a propyl group on the other side. So there would be your letter A. Letter B, butyl acetate. Acetate is the 2-carbon original carboxylic acid, and then we'd have a butyl group with a 4-carbon chain. Letter C, hexane 08, 1, 2, 3, 4, 5, 6. There's your ester linkage, and on the other side would have an ethyl group. And in letter D, benzoic acid, that's our aromatic ring. And on the opposite side would be a methyl. So I can give you your structure corresponding to each name just from a missed slide earlier. Hey friends, that concludes our first 2 sections of our chapter. When ready, come on back and you can start where we left off with the physical properties of carboxylic acids, esters, and amides. You've been working hard, take a little break.